All right, hello everyone. So today we're working with a calculus 1 problem. Have a polynomial f of x equals 3x to the fourth minus 12x cubed minus 54x squared plus 4x minus 1. We're asked two things: to get the inflection points, if any, in intervals f of x is concave up and or concave down. So let's recall what an inflection point is. So an inflection point, I'm calling that x sub 0, is a point for which your function is continuous and the concavity changes at that point, x sub 0. So I drew a couple graphs here in red. For the first graph, your graph is basically concave up, although from left to right, and then going right at x naught, it's concave down. Okay, and likewise on this other graph, your graph is concave down, and at x sub 0, it becomes concave up. Okay, so that's what an inflection point looks like. Now, the way you're going to find these is related to how we find the concavity. Is usually we take the second derivative, and we're going to follow these two facts, that if your second derivative is greater than 0, then f of x is concave up, and if your second derivative is less than 0, then f of x is concave down. So we're going to work with that. We're going to take a couple derivatives, but before you do that, you always want to find the domain of the original function. In this case, it's a polynomial, so the domain's all real numbers. The domain has no restrictions on it. And the reason for that, just for practical purposes, is because you're going to eventually make a number line. And on this number line, you got to make sure that you note any restrictions that your function might have in terms of the domain. So if I make a number line and I include something that is not really part of the domain, then that number doesn't really belong. Whatever that, if you plug that number into, let's say, your second derivative, but that's not part of the domain, that does not give you some valid information about, let's say, the concavity, like it is in this case. So that's why I'm saying that. So always make sure you have your domain, and again, you're going to build a number line from that. All right, so let's start with taking derivatives. Our first derivative would be 12x to the third minus 36x squared minus 108x plus 4. And then our second derivative will be 36x squared minus 72x minus 108. And yes, the 4 will be gone, just like the minus 1 up here, because it's a constant. Now, we have our second derivative, and to find inflection points and information about concavity, you're going to look at the following. You're going to look for places where the second derivative equals 0, or where the second derivative is undefined, but your function is continuous. Okay, so how do I find where the derivative is equal to 0? Well, we're going to set the whole derivative equal to 0, essentially. So f double prime of x, 36x squared minus 72x minus 108. We're going to set all of that equal to 0. I'm sorry, I'm just going to make sure that I down, yes. And now, notice how 36, 72, and 108, 36 divides everything. And I'm going to factor that out. Do you need to do that? No, you don't. However, I recommend you do that just because of the fact that when you factor a number out and you're solving for an equation, that makes it a lot easier. And yeah, if you didn't see 36 right away, I mean, if it takes you a minute, you saw 4 or whatever, first then do that. But if you can, kind of factor out basically the greatest common factor out of all of these. All right, so you factor 36 out and you get x squared minus 2x minus 3. And I'm going to factor that polynomial further. Okay, and this would be x minus 3 and then x plus 1. And again, I'm going to set that whole thing equal to 0. Second derivative is what I meant. And you get two answers, x equals 3 and x equals minus 1, because I would set each of these factors equal to 0. And our number line is going to have negative 1 and 3. So right, so after you find your points, you're going to make a number line. You'll place those points there. And the second type of point, so we got where the second derivative was equal to 0. Are there any points where the second derivative is undefined but f of x continuous? No. The second derivative is a polynomial again, so it's not, it's defined everywhere. So yeah, we're not going to worry about those. And what we do, very similar to maybe when you're finding relative extrema with a line, number line, you make these intervals and you pick points out of each of these intervals. So for a point that's greater than 3, I'm going to pick 4, between -1 and 3, 0, and -2. And a quick word on this, there's other ways of doing this. Other ways are by kind of just looking at the numbers, the intervals, and looking at the second derivative and seeing how it would become become negative or positive depending on the numbers. The reason I'm saying this is that instead of picking numbers, there's some professors out there that don't like this method, okay? So just be aware that if it's your professor, you got to do something else. But this method, yeah, I would say it's accepted by a lot of professors, so go ahead and use that. So I'm going to go ahead and take each of these points, and each of these points I'm going to put into the second derivative. And the sign that I get from each of the points plugged into the second derivative gives you the sign of the whole interval. Okay, that's like the nice part here. Now, where should I plug this in? As I said, yeah, it's the second derivative. You could certainly plug it into the original second derivative. However, you could also plug it into the version that you see that I just circled. 36 times quantity x minus 3 times quantity x plus 1. I'm going to put it in there. I'm going to put 4 in there to be more specific. And why am I doing that? Well, you have 36. 4 minus 3 is 1. It's positive. 4 plus 1 is positive. At the end of the day, I don't care what number I get when I plug these values in. I care about a sign. So 36 is positive times a positive times a positive. That all comes to be something positive. So I'm going to put a little bunch of positives here. When I plug in 0 now, we get 36, 0 minus 3, 0 plus 1. This becomes 36, 0 minus 3 is negative, 0 plus 1 is positive. Yeah, but if you prefer to say 0 minus 3 is a minus 3 and 0 plus 1 is a positive 1, totally fine with that as well. So positive times a negative, 36 is positive times a negative number is a negative, times a positive is a negative, so this is going to be negative, less than 0. So we're going to put a bunch of little minuses here. And finally, when we plug -2 in, it's going to be 36 times minus 2 minus 3 is a minus 5, so it's negative. Negative 2 plus 1 is a negative 1. So positive 36 times a negative is a negative, times another negative is a positive. Okay. So we'll put a bunch of pluses there. And yeah, do we have an inflection point? In fact, we have two. You have one at -1 and you have one at 3. Okay. So our inflection points occur at -1 and 3. And also make a note that these are the points where the x's of these points. When I say point, it's really an x and y. So what you need to do, which I will not do though, is you need to plug in each of these points, just because, yeah, just save time. You need to plug them back into your original function to figure out what the y value is at -1 and 3. Okay, so that, because technically, right, when you're looking for a point on a graph, there's an x coordinate and a y coordinate. And then the intervals where your function's concave up and down. So it is concave up all the way from -infinity to -1. And then union 3 to infinity, so that's where it's concave up. So I'm just going to say CU. And then concave down, it's going to be from -1 to 3. Okay, so there we go. All right, so, and that's pretty much how you do these problems with any type of function. I have another video out there where I do the same thing, but with a logarithmic function. It's a combination of a logarithmic function times a polynomial. So I'll try to link a video to that and check that out. Okay, thank you so much for your time, and I hope this helps.